2.2, change in linear and exponential functions. Okay. I can zoom in like this for live while y'all are right here, but it just doesn't catch that when we're recording. It doesn't understand. Okay, so those of you that were absent yesterday, this will make a whole lot more sense after you watch yesterday's lesson. But we're going to have to rock with it today as if you understand already. Okay. It says in the last section, we learned that, what's the word? Arithmetic. Arithmetic. It looks like arithmetic. Arithmetic is a noun. Arithmetic is the adjective. Arithmetic sequences behave like linear functions. Linear functions. And that geometric sequences behave like exponential functions. Exponential functions. Okay. It says we will look more closely at these connections today. We looked at yesterday arithmetic sequences. We've got two different equations for arithmetic sequences. Okay. The top one is really my favorite. Okay. It says I can find any value a sub n. So this is the output. A sub n is going to be the output. I can find any output value if I plug in any input value in. Any input value in. Okay. A sub 0. A sub 0. That's the starting point. That's the initial value. Okay? Initial. The 0 stands for the first position, the 0th position in line in the sequence. Okay. So when we're talking about like a sequence of numbers, we're talking about a bunch of numbers in a row, in order. N is the position of the number. So like if it's the third number in the sequence, N would be 3. Okay. So the output's going to be what number you get after that. A sub 0 is the first number. It's the initial value. Okay. What do you think D is? The difference. We call it the common difference. Common difference. So if we slide over here directly to the right, you see old school f of x equals b plus mx, or mx plus b. They wrote it like b plus mx so that you could recognize it as the initial value. A sub 0 would be b, your y-intercept, right? It's the number when x is 0. And then m, if that's the case, corresponds with what? D, the common difference. The common difference, the slope. And x is your input, and f of x would then be the output. Okay? So this is not hard. It's not much different. We looked at yesterday when we graph arithmetic sequences, they come out as discrete data points. The reason for that is we can't input any other numbers but whole numbers. So if my input can't be anything but whole numbers, then my output is going to also be discrete data. Discrete meaning dots. So the difference in graphing an arithmetic sequence and graphing a line is when I graph a line, I draw a line. When I graph an arithmetic sequence, I plot the points, and you don't put the line through them. Okay. We've got another set of equations down here. A sub n is equal to a sub k plus d times n minus k. This is what I would use if they gave me 2 points. If they gave me 2 points, I would want to use this one. The other one works if I have this common difference, the slope, and the initial value, the y-intercept. That would be my slope-intercept form. The second one I want to use if they give me two different points. Say they give me a sub n and another point a sub k. Look what that looks like. Do you see that it mirrors point slope form? When do I use point slope form? When I got 2 points. Wow. Okay? So not complicated. A lot the same thing. Let's move on down to geometric sequences. Geometric sequences. So we learned yesterday G sub n. G sub n is equal to G naught times R to the n power. Geometric sequences are exponential. I can tell that they're exponential because x is in my power. Polynomial functions have x to some number. Exponential functions have a number to the x power. You see the difference? Polynomial functions have x to some power of a number, like x to the fourth. That's quartic. X squared, that is quadratic. Come on, Algebra 2. X cubed is cubic, right? X to the third. Those are all polynomials. The difference in a polynomial here and what we're talking about now is polynomial have number for the base. Polynomials have number for the power. Exponentials have number for the base, x for the power. Okay. On the first equation that they gave me, I see G sub n. Again, that's your output. If you want to write that down, G sub n is your output. G sub 0, what's that going to be? Initial. What do we call R yesterday? In Algebra 2, I taught you that's the growth or decay rate. What do we call it? It's the ratio, the common ratio. Common ratio. That's R. And then this little bitty n up here, what's that guy? It all depends on that. That's the position or the input. Input. So depending on my input, I might get a very, very different output. The ratio should be the same no matter where I am on the function. And my initial value is 1 point at x equals 0. If I compare that to these over here, do y'all remember these? A times b to the x. If b is greater than 1, what do we have? Growth. Quit saying no, you remember everything. If b is greater than 1, we have growth. If b happens to be a fraction or a decimal, decay. Decay. Y'all remember this? Have you learned this before? I believe so. Okay. Probably the most useful of the geometric sequences is the second one. G sub n equals G sub k times R to the n minus k. Why would that be useful? When would that? If I have 2 points. If I have 2 points, this is the one I want to use. If they give me 2 points but not R, so they may give me a point n comma G sub n and k comma G sub k. We can plug and chug whatever information we've got. We can find R, and then we can write the ratio or write the expression. Okay, this is if they give me 2 points. This corresponds with the version that you've seen for exponential functions. F of x equals yi or y1 times r to the x minus x1 if I had a point. x1, y1. Okay? All right, so now let's just make some comparisons. It says it's important to recognize and understand the similarities and differences between linear and exponential functions.
They both have an x.
Okay, they both have an x. Yes, they do. What's the domain for a linear function? Domain for a linear function. Let's write that out. Domain is all real numbers. That double-barreled R. Domain is all real numbers. They're continuous. They go forever and ever to the left and right. No asymptotes, no holes, no janky anything. What's the range for a linear function? Also, all real numbers. Linear functions?
My bad. I thought it was about X.
So for the parent function, y equals x. All real numbers, all real numbers. But an exponential function, it's not necessarily going to have a hiccup in the x direction. Not going to be undefined necessarily anywhere, right? Even if the power is negative, that's just a fractional exponential function. It's still fine. Exponential domain is all real numbers. Exponential range for just the regular parent function, y equals b to the x. So let it be a positive base, a positive x power. Range is going to be, he says, all positive numbers. Let's say y is greater than or equal to.
No, because you can't touch. That is an asymptote.
Y is greater than 0. And that comes back to the thought that as long as there ever was pi, there will never be no pi, right? Even if I'm halving, say I bring in a cookie and I half it, and then I half it again, and then I half it again, and I half it again, and I keep doing that so many times, eventually I have this minusculous little piece that only my little mouse would want, right? But there's still a piece. As long as I ever had cookie, I will never have no cookie. I will also never have negative cookie.
Is he still here?
Yes. We're working on it. Okay, another thing for linear functions. Over equal length input values, output values change at a constant rate. That's how you're going to know. You're going to see that if they're adding or subtracting by the same number every time in the table. For exponential functions, they change proportionally. It's not at a constant rate adding and subtracting, but if you were to go in and divide, you would see the same number every time. So you're going to see that based on multiplication. Does that make sense? Okay. If you have 2 points, you can write a linear expression and you can write a geometric expression given 2 points. Ready to go on? All right. So for example 1, our instructions say selected values of several functions are given in the table below. For each table, determine if the function is linear, exponential, or neither. It's got to increase by the same amount on the same intervals of x. So over equal length x intervals. So my first check is just going to be to make sure that those x intervals are doing the same thing every time. Are they on the A? Okay, they're all increasing by 3. So we have equal length x intervals. That part's out of the way. Now we got to go look at y and see what it's doing. Decreasing by taking off 2 every time. Taking off 2 every time. Subtracting. Add or subtract means it's linear. Linear. So we'll decide at this point that this one is linear. It's arithmetic, not aromatic, but arithmetic. It's arithmetic. And what's the constant rate of change here? Okay. Constant rate of change, I would say for every 3 x's. So it's not negative 2 over 1. It would be over 3. Something like that. Okay. All right, let's go on to part B. On part B, I see 1, 2, 3, 4, 5. So we have equal length x intervals. That's your first check. Second check, is it adding or subtracting the same amount every time? No, because I got plus 1, plus 3, plus 5, plus 7. Okay, that gets a little crazy. So we know it's not linear. Now my check is to see if I divide, do I get the same ratio? So I would do 16 over 9. I don't know what that is. Moving on. 4 over 1. Well, 16 over 9 is not 4. It's not 4. So we're done. It's neither one. Yeah, I got 16 over 9. I'm going to move on and check my next numbers, and then I might come back to that one and see if they're equal. I'm not going to try to compute 16 ninths at this point. Is it? Nope. 4/3? No. No. It is not 4/3. All right, let's go on to C. It's not 4/3. He divided the top by 4 and the bottom by 3. You can't do that. Now, letter C. Do we have equal x intervals? Yes. Okay. So then I look at my y's. Am I adding by the same amount every time? Or subtracting by the same? So it's not arithmetic. It could be geometric. So let's start with ratios. For the ratios, I always go bottom to top. Okay, I always do 16 over 8. No, not 1/2. What is it? 2. Not 1/2. Welcome to pre-cal. 8 over 4. 2. 2 over 1. Also 2. So I have the same ratio every time. The ratio is 2. That means my numbers are increasing. They are doubling. Can you tell? Okay, so because the ratio is 2, what could we say about the sequence? It is geometric. Are y'all able to see this well enough? Is this okay? Yes. It's geometric. I think this is better than me writing up there with the expo marker. Yeah. Sort of.
You're saving expo markers.
All right, letter D. Not on YouTube, man. 5 to 10 to 15 to 20 to 25. Same equal x intervals, okay? What about our y values? What's happening? 5 over 10? It is half. 10 over 20? Half. How about 20 over 40? 40 over 80? Half. So we're seeing a half growth rate, or a half decay rate, or a common ratio of 1/2. So what we know is it is geometric. You like this? Okay.
I'm sure it gets worse.
Awesome. Enter example 2. I've done this example 4 different ways, and I don't like any of them. And my paper looks like this. And I've subtracted a whole, or erased a whole lot, and it still looks like this. Okay, so it says a wild rumor is spreading that Mr. Passwater won 3rd place in the World's Strongest Man contest. Whoa, Mr. Passwater probably didn't start the rumor.
I think you did.
The number of people that have heard the rumor can be modeled using a geometric sequence, where 43 people had heard the rumor on day 3. Okay, so by day 3, that's input, day 3, output is 43 people. 140 people have heard the rumor on day 6, 140. It is geometric, that's what they said. According to the model, how many people to the nearest whole number have heard the rumor by day 10? So we need a function. We need a geometric function so that then we can plug in the 10. We need our right equation for 2 points, geometric function, because here we don't have the ratio. And we can't find the ratio because we don't have equal length x intervals or whatever it is that we're supposed to be able to use to find the ratio. Okay? So we got to go with the 2-point function, g of n. I'm going to write it above example 2 because we're going to need some space. It is kind of point slope form, but it's applied to exponential functions. G of n is equal to g of k times r to the n minus k. You'll see what we're doing here? Now I would label my 2 points as one of them being the n's and one of them being the k's. And here's how I made my decision. In the power up here, it's n minus k. I want the bigger number to be my n. Okay? N is the input. So 6 needs to be my N stuff. So N and G of N. Or G sub N. That's really how they write it in exponential world. G sub N. And then for my K, 3 is K. 43 is G sub K. Y'all with me on that? So now we can plug in. For G sub N, we got 140 equal to 43 times R. I don't know R. To the, we want 6 minus 3. I tried to color code so you could see exactly where these numbers are going in here. No. So you can't combine, wait, 140 and 43?
Yeah, can you divide 43 away from R?
Oh, can you divide? I thought you said combine. Yeah, we're going to solve for R. Okay, so we're going to first divide 140 by 43. Okay, I'm done with the color switching, whatever. If y'all can't plug in, it's over. Divide by 43 on both sides. So we've got R to the what? R to the third. 6 minus 3 is 3. R to the third is equal to 140 over 43. We're going to take the cubed root because it's R to the third power. If I take the cubed root, that's the same as raising it to the 1/3 power. We're going to raise it to the 1/3 power. So R is actually equal to 140 over 43 to the 1/3 power. Yeah, now we can write our function. We have R. Okay. And we're trying to do a prediction by day 10. I would stay in this double point formula. Okay. Choose one of your values for G sub K. Which point would you like to use again?
43.
The smaller one? Okay. So we already called it K and G sub K. So let's do G sub N now. G sub N is going to equal G sub K, which is 43, times what is R? 140 over 43 to the 1/3. And that would be raised to the N minus K. So open parentheses up there. What's N? 10. Or what's K would be, it's going to be N minus 3. N minus 3, not 10 minus 3. N minus 3. Because right now we're just writing our function. In a second we're going to plug in the...
Oh, okay.
Oh, that's a bad idea. Yeah. So N minus 3. Is that making sense? Nope. So right now we've got G sub N equals, we know R is 140 over 43 to the 1/3. So we plug that in for R. We have 43 and 3 for G sub K and for K. Is that making sense? Is that better? Now we have a G sub N sentence. We want to know what is G sub what? 10. So we're going to have 43 times 140 over 43. Watch this. If I push that 1/3 through, that's going to be to the 1/3 times 10 minus, what's 1/3 times 3? 1? 10/3 minus 1? You should be able to put this on your calculator. 43 times 140 over 43. Well, it was 1/3 times n minus 3, or 1/3 to the n minus 3 power. When I raise a power to a power, I multiply them. So I distributed 1/3 times n, which is 1/3 of 10, because n is 10 this time, and 1/3 times negative 3. 1/3 of negative 3 is negative 1. So on my calculator, I should type 43, open parentheses, 140 over 43. Not everybody at once with all of your calculators that you've been gifted. On your calculator, give us a minute. 43 times 140 over 43.
Would it still work if we did it?
If you didn't, yeah, but you'd have to raise the 1/3 to the power. You do power of a power.
That's what I do. Can we shut off the
Not yet. You should have all of this on your calculator.
It's gonna be like 4 or something.
No, not on the 10th day.
It's gonna be like,
Oh, it's like half.
We're trying to figure out.
my guess is like 1,200.
We're trying to figure out how many people have heard this rumor by day 10.
Am I close?
Yeah, I don't even know.
We have a winner answer. Y'all ready to hear it? I think round up.
You can't really, this is
675.76 of a person. Let's call it 676 people. 676 people. I think this R is ridiculously complicated. I have not ever seen an R or a growth rate that was 140 over 43 to the 1/3 power. Okay? I don't think it'll be like that moving forward, but the process is not any different later. You got to plug in your points, solve for R, write a function, plug in a new point.
Well, at least nothing that's on the y side, right?
No. Okay, let's do the last question before y'all start getting restless and putting up and doing all the things. The last question is a flashback to maybe 8th grade. It says, a large theater has rows of seats where the number of seats in each row can be modeled by an arithmetic sequence. Arithmetic means linear. If the 5th row has 31 seats and the 11th row has 49 seats, determine how many seats there are in the 25th row. Yeah, so what are you doing, David? He's saying y2 minus y1. What are you finding? Slope, or the average rate of change. Haven't we learned that before? So y2 minus y1. One common mistake I saw on the unit 1 test is we did x's over y's. No lie. I saw that several times on that unit 1 test. You would go in and you would do y's over x's, or you would do it backwards. So 49 minus 31 over 11 minus 5. 18 over 6. What's m? Now what?
You would have to make a statement. You're just plugging 3.
Right? How do we make our statement? We know m is 3, but what else? You could use point slope. You could go slope intercept and solve for b. What do you want? Make a choice. Slope intercept or point slope? Slope intercept. All right. So we got y equals mx plus b. What is your favorite point, Ruth?
0.
You have 2 points to choose from, 5, 31 or 11, 49. You want 5 and 31? Okay, she picked 5 and 31. So y is going to be 31 equals, what's m? 3. What's x? 5 plus b. So 31 is 15 plus b. Keep going. Subtract 15. 16 is B.
It's 18 over 6, 3. Is that what the 3 came?
18 over 6 is 3. That's where we got the 3. Good question. Okay. So we've got 16 for B, and earlier David said we've got to write a function. We've got to write a function before we can plug in the 25. So what is our function? Y equals 3x plus 16. And we are interested in how many seats there are in the 25th row. So we want f of 25. Notice that I went from y to f of because I'm plugging in. F of 25 is 3 by 25 plus 16. Say it louder. 91. 75 and 16. 91 what? Seats. 91 seats. Okay. Okay, so I'm going to stop the recording at this point. That is all of the second lesson.